So linear regression, we have to define x and y more precisely. Y is called the dependent variable because we want to determine what y is based on x value that we already know. So x is called the independent variable. So we have to define what an independent variable is, and that independent variable is supposed to have some kind of relationship with y, the dependent variable. Another way of saying the same thing is dependent variable is also called response variable in the ANOVA context. An independent variable is also, you can refer to it as predictor variables also. So it is a predictor variable that predicts the value of y. So we have, in the case of simple linear regression, we'll have only one predictor variable, one independent variable, and then we have the y. So we want a relationship between x and y, and that will look like this: beta sub 0, the y-intercept, plus a slope coefficient times x, the independent variable, plus a random error. So when we have only one x variable in the regression model, it is called simple linear regression. But when you have multiple x's, so beta sub 1 x sub 1, beta sub 2 x sub 2, beta sub 3 x sub 3, and several x's, and that is called multiple linear regression. In chapter 12, we're going to look at only simple linear regression model. In chapter 13, we will extend it to multiple regression model. So here is what individual y values will look like in a simple linear regression model. So you have x variable. For any given x variable, there is a mean value which is determined by beta sub 0 plus beta sub 1 x, plus there is an error term, and that determines the actual value of y. So when you plot just this part without the error, that is this red line, that is called the mean of y. The mean of y is determined by this straight line. The actual value of y is given by, for each x, finding the mean and then adding a random error term. Now given sample data, now how do we estimate what beta sub 0 value is and what is beta sub 1 value? And this is called simple linear regression equation, where we have a predicted value for y that is based on b sub 0 plus b sub 1 x, b sub 0 being our estimate for the y-intercept, and b sub 1 is the estimate for the slope coefficient. So the question is, how do we come up with these two estimates? Okay. And we're going to use what is called least square estimate. And here once again, we have the actual plotted points between x and y. Now we can define the actual value of y as the predicted value of y, which is b sub 0 plus b sub 1 x plus an error term. Now given these points from the sample, the least square estimate is that b sub 0 and b sub 1 value for which the squared error, the sum of squared error, is the minimum. So this is the, if this is the estimated line, this is the error for this point. That's the error for that point, and here is another error. So some errors will be positive, some errors will be negative. So to make sure that the positive and the negatives do not cancel each other out, we square the errors and add them all up. So that's your sum of squared error. So we want to find b sub 0 and b sub 1 value for which the sum of squared error is the least. And that is the reason why this is called least squares estimate. So in other words, we want to minimize the squared sum of the error. So like that. So we can state the problem of least squares as finding the b sub 0 and b sub 1 value for which this sum is minimum. And it turns out that by using calculus we can derive that formula. Here are those formulas. B sub 1 is given by SSXY over SSX, where SSXY is given by this. So multiply x and y, sum those, then subtract sum of x times sum of y over n, and s as x is given by this formula. Okay. Once you find b sub 1, then we can find b sub 0 using this formula. So when we use these formulas to find b sub 0 and b sub 1 values, then we are guaranteed that when you substitute those values for b sub 0 and b sub 1 in this formula, this sum of squared will be the least possible value. There is no other b sub 0 and b sub 1 value for which this sum will be smaller.